Now let's see the effect of the leakage inductances and the model of the loosely coupled coils will have on our wireless power transfer system. So as we know, we have a primary side coil that's coupling magnetic field to a secondary side coil. Now if we replace these loosely coupled coils by their equivalent model, as we said, we have an ideal transformer at the heart of the model. Of certain turns ratio, N1, N2. And then we have a magnetizing inductance on the primary side that's equal to K, which is the coupling factor between the two coils, times L1. And then we have a leakage inductance in series that's equal to 1 minus K times L1. And on the secondary side, we have leakage inductance equal to 1 minus K times L2. So now it's obvious the effect of the leakage inductance. So as we increase the distance between the primary and secondary or change their orientation, essentially the coupling factor between or the factor of the coupling between the primary L1 and L2 essentially is going to decrease from 1 all the way to 0. So as we increase the distance or change the orientation, let's say increasing the distance between both coils, essentially the coupling factor decays from 1 to 0. And so essentially the series inductances at the primary side and secondary side, well, what will happen, they will increase, while the magnetizing inductance is going to decrease. So as you can see here, we have a voltage divider established by these two inductances. And essentially this voltage divider is going to reduce the amplitude of the voltage across the primary side of the ideal transformer, this voltage here, which ultimately is going to reduce the voltage and power that's delivered to the secondary side and eventually to the DC load. So to solve this and tune out these leakage inductances, these series inductances that cause the voltage division effect and essentially choke the amount of power that we can transfer from the transmitter to the receiver or from the primary side to the secondary side, we connect a capacitor C1 in series with the primary and another capacitor C2 in series with the secondary, such that the value of C1 can be found from the fact that we want C1 to resonate with the self-inductance of L1 at the resonance frequency. So basically, or at the frequency of operation. So omega naught square is going to be equal to 1 over L1 C1. And so C1 is basically going to be equal to 1 over omega naught square L1, right? Where omega naught square, since we are discussing resonant wireless power transfer, is equal to 2 pi times the resonant frequency for the standard we are studying is 6.78 megahertz. Okay, and similarly, the value of C2 will be equal to 1 over omega naught square L2. So if we select C2 and C1 in this way, all of the leakage inductances will be eliminated. And what we will find out is, as we know, the equivalent input resistance of the full bridge rectifier is equal to 8 over pi times pi squared times the load resistance, the DC load resistance R, and let's call this resistance Rn. That's the equivalent input resistance of the full bridge rectifier at the receiver side of the wireless power transfer system. And so under the condition of using C1 and C2 in series with the primary and secondary side respectively, such that their value C1 is equal to 1 over omega node square L1, and C2 is equal to 1 over omega node square L2. And if we calculate the equivalent input impedance seen by the half bridge, we'll find it actually resistive, and it's equal to omega node square we'll find this resistance we'll find the resistance seen by the half bridge rectifier essentially equal to, under the resonance condition, omega node square times m square divided by Rn, where Rn is the rectifier equivalent input resistance. And what is M? M is basically the mutual inductance between the two coils, and it's equal to K times square root L1 times L2. Okay, so basically the half under this resonance conditions that I just mentioned, and we select C1 equal to 1 over omega node square L1, and C2 is equal to 1 over omega node square C2 under this L2, sorry. Under this resonance condition, essentially we'll find that the equivalent impedance seen by the half bridge inverter is basically going to be real, and its imaginary part will be equal to 0. All right. And so if we just try to look, instead of this impedance, if we try to look at the equivalent impedance after the capacitor, so when we move after the capacitor, what we'll see L1 of the primary side of the transformer, because L2 is already cancelled using C2, right? So the equivalent impedance is seen here. Let me write the equivalent impedance seen by the half bridge first. It's going to be real equal to omega node square m square divided by the equivalent input resistance of the full bridge rectifier. On the other hand, if we move after C1, we'll find that the impedance that we will see is basically is going to be omega node square m square divided by Rn. We're just going to add the impedance of the primary side of the coupled inductors, so J omega node L1. And why did I calculate the equivalent impedance seen by the capacitor in series with the half bridge inverter? Because in this way I could model the transmitter side in a simple way as half bridge S1, S2. This is the DC input voltage. Then we have the capacitor C1, and then we have an inductance L1, and finally we have a real resistance equal to this value, or omega node square m square divided by Rn. And that's essentially the equivalent model of the entire power transfer system with respect to the input side, or you can say it's the equivalent model of the transmitter side.